Everyone, thank you for coming in this evening. It's an absolute pleasure to welcome Jim Eyre back to the AA. Longtime friend, indeed, graduate, past president, former council member, former honorary treasurer, and current chairman of the AA Foundation here at the association. Wonderful to welcome Jim back, who will present this evening a lecture titled How to Make a Hothouse Cool. An opportunity for Jim to present some of the latest work and thinking of the office that he's a co-founder of, Wilkinson Eyre, here in London, and which will focus largely on a single project this evening, if I understand it right. And I think that on its own marks an interesting point of tonight's conversation, which is, of course, the presenting of not just a single project, but what by almost any reckoning we would all agree is quite an unusual project. And I think it's a wonderful chance for us to see the many facets and dimensions to that particular project. And as I was thinking about it, what's interesting is the way in which the project we'll see this evening, which is in effect a project that is the commissioning of Singapore's, you could call it, National Botanical Garden, is happening at a moment in which architectural careers, interestingly, are being shaped by the demands and realities of what you could call our extreme one-off ambitions. And this is a striking, striking example of that, a project that not just in its brief or its program, but also its siting, a botanical garden in the center of a rapidly growing city on reclaimed land, and with contents that are almost unprecedented in the combination of pieces, is really emblematic of where architecture is today, beyond just the remarkable achievements and accomplishments of the building itself. Architecture today is being defined increasingly by anything but the expected typology or type. Architecture is dominated increasingly by the rise of new and unexpected challenges in almost unknown and unexpected places. Architectural careers, as we all know, to a stunning degree, are shaped project by project, and we learn architecture by the doing of single undertakings. This is the sort of extreme version of that, you could say, today, and a generation of architects have come of age in which that reality is, I think, taking place in ways that are almost unbelievable in the challenges they put forward. Architectural histories, as we know it, are written, in fact, project by project. So in a way, this is part of a long condition of architectural knowledge itself, that to an amazing degree we all learn architecture just one project at a time. When one confronts the kind of realities of gardens by the bay, of course, what we see is the stakes are, in fact, even more extreme today than ever before. I think what the project absolutely builds upon, without talking about it in too much detail, are long-running interests and ambitions of Wilkinson Eyre that have been in place for many years. The pursuit of absolutely precise, highly, highly refined, indeed elegant structures and spaces, which has been a hallmark of the office since its founding a quarter century ago. The fact that they pursue what we would all think of as technology at the intersection between art and science, and that architecture lies in the management of those potentials, is another strong trait of not just this project that will be highlighted tonight, but for many years within the office. And finally, that building structures as we know them are part of larger environments, and in fact they are environments, and the controlling of those environments and their ability to respond both internally and to the larger conditions they're put in is, again, something that this project builds upon from many years of experience and accomplishment within Wilkinson Eyre. As I said, it's an office that founded now, I think, almost exactly a quarter century ago, in the late 1980s. In about 1987, Jim and his partner, Chris Wilkinson, come together and begin to form a group of collaborators that have pursued the work that tonight's project is the latest example of. It's an office that's achieved remarkable buildings over the years. As you all know, the recipient of many awards, and was certainly the Stirling Prize almost exactly a decade ago for their Gateshead Millennium Bridge, a highlight of that career. They have been the subject of many publications, monographs, and exhibitions in this country, and worldwide. And it's a real pleasure, 5 years after we had Jim and his partner and other collaborators into the building for the launch of a monograph of their work, to invite you back and to show the latest results. So please join me in welcoming Jim Eyre.
Okay. Thank you, Brett, for that kind introduction. I think we're known as architects for our close relationship with engineering, I think, out there in that big wide world, or the marketplace, if you want to put it another way. But in fact, we don't employ any engineers at all in the office. We're all architects. Sometimes I get, Jim, are you an engineer? Are you the one that's an engineer? And I don't know whether to take it as a compliment or to be insulted. I can never quite work out. I'm always slightly disappointed. But I do usually reply by saying, well, I can understand what engineers do, and I can draw structures that I know will stand up, they're the right size, etc., but I couldn't even begin to calculate them. So I'm definitely not an engineer, but I think what it does tell you is that as architects or designers, we are able to cross disciplines, actually, and it's very much a part of the way that architects work, and I think should work, and also engineers should work similarly, should think about architecture. But before talking you through the Singapore project, I first want to just talk about or explain how some of our interests in architecture have been evolving, and how they inform the way that our architecture looks, our particular preoccupations, if you like. And I'm just going to use some examples, just a very few examples of some of our projects, which I think have, relate to particular themes, but also in some cases have particular relevance to the Singapore project. And it's not intended, this lecture is not intended as a thesis or a treatise on architecture in any way. It's just an opportunity to tell you about what Brett has described as a very unusual project, so you can get an insight into its genesis and how it works. But I think it does touch on some important issues for us all as architects, how we handle destinations, the places that people go, whether it's just purely for enjoyment or whether it's to what I might describe as acquiring cultural capital, this body of knowledge that you can say you've been to these various places. But also, it really does touch on our relationship with nature, and then, of course, how we deal with the big issue of climate change, which faces us as architects and society, of course. So to start with nature, this is an image from a performance artist called Dennis Oppenheimer, this piece is called Parallel Stress, and it was done in 1974, where he set up these two blockwork walls next to Brooklyn Bridge in New York and spanned them by themselves. I quite often use this in bridge lectures, actually, but that's the sort of obvious one for bridge lectures. But I think the real point is it's just a reminder that in nature, you can't fight nature. You will fail. Ultimately, you will fail. And that every material that's made is trying to return to its natural state. If you think about iron, it gradually rusts away until it becomes what it was when it came out of the earth. And it's just a kind of reminder that we have to work with nature rather than fight it. Our own interest in nature, I think, has always been there in terms of the admiration of the kind of light structures that you get in nature, whether it's trees or whether it's extraordinary shells or little spiders' webs or whatever, or here on the left the manta ray, the beautiful form, the functional form. But I know that we've been asked from time to time, people, I can't remember who it was now who did a book on zoomorphics, and they're pushing us to say how natural objects had inspired our architecture. And I kept saying, well, no, it's not. It doesn't work like that. It's on the contrary. What actually happens is you design something, and then you find something in nature that resembles it or has some sort of empathy with it. So it is kind of the other way around. It's not that nature's an inspiration, but it's just that nature's kind of done it already, basically. And it's just always interesting to see, to make those comparisons, to find those, in a sense, illustrations that are saying something that you wanted to say with your architecture. So here, lightness and being lighter than air. The gossamer albatross thing was something I remember as a student thinking this was the most amazing thing, the bicycle, pedal-powered aeroplane crossing the channel. But in fact, as an architect trained in the 70s, growing up as an architect in the 70s, first at Liverpool and then here, nature was actually at the bottom of my list of things that I was interested in as an architect. We never really looked at nature. We didn't look at landscape particularly. We did look at the urban form, but we were very much involved in what you call high-tech and the sort of the building as an object in its own right. And for us as a practice, the first project that came along that we won was to look at a master plan for Kew Gardens. This is an 18th century image of Kew Gardens, and you'll see actually it consisted of two gardens. There's Capability Brown on the top and William Chambers on the bottom. That shows two completely different attitudes to nature. Capability Brown, it's the house that it related to, is over here on the left, and Chambers, it's the White House, and Kew Palace is on the right at the bottom. So the bottom one is all about perambulating around the garden, your after lunch walk, and come back to the house for tea and see these little pavilions that have been built, most of which are still there. And Capability Brown was trying to simulate the natural landscape, and the two kind of clash. Our project was actually to do with how do you tie all this together, how do you improve the way that people move around the gardens, as well as rationalising all sorts of things. They had sort of 400 people in a kind of archipelago of spaces. But it was interesting just to see how the underlying geometry, which is the blue in the original Nesfield design, and then this red arc, which I kind of devised as something that might potentially link the two halves of the garden. And of course what's happened since is that there's been a series of projects, so we identified a series of initiatives on this arc. At least two of them have been built. John Pawson's stunning bridge across the lake, and then Mark's Barfield did a treetop walk. And part of that project was this developing this sort of kind of understanding that you hadn't really given much thought to. This is a diagram that I nicked from a description of zoos and how attitudes and the way that sort of zoos work, our relationships with zoos work, how it's evolved over the last few centuries, because it applies just as well to botanical gardens. This idea that the Victorians went around collecting everything. Everything's really interesting. Find out more, gather more knowledge. To the 20th century, where you were kind of we thought we could manage habitats. To now, quite clearly, we're really just talking about survival and conservation. And up till then, as I said, we were kind of high-tech architects, and I show this. This was our first sort of major building, was Stratford Market Depot on the Jubilee line, designed in the early 1990s, which I'm still very pleased with. But I remember telling our team, most of whom are still with us, I said, I don't want to see a single piece of wood in this building anywhere. You're not to have anything hidden behind anywhere, as a sort of spacer or anything. It was almost a sort of, it was crazy, but it was just that I really felt that this kind of architecture should all be about metal and glass and engineering, if you like. So we've come quite a long way since then. And now we're terribly interested in natural materials. And I think for lots, you could just call it old age, actually. I think it does happen, it does gradually happen to you, that you develop, that you recognise the beauty of natural materials and working with nature. And we're doing a project for a Maggie Centre at Oxford, at the Churchill Hospital, which is a bit of a tree house. But actually this is This is using advanced technology with wood, engineered timber, with a company called Forest. So it's all completely prefabricated, and when it goes on site, it'll happen very quickly. So, and then the next thing I wanted to just mention was context. As architects, we don't now, certainly if we did before, we certainly don't now think of our buildings as object buildings in anonymous townscapes or landscapes. And in fact, I spend a lot of my time at the moment working on what's called the new Bodleian project at Oxford University, which is Giles Gilbert Scott's building here in the foreground, which was built as a depository for books. It's got sort of 16 stories of books storage in it, which is in Broad Street, right on the sort of historic centre of Oxford, and this is where the university started. So these are the Bodleian buildings. So you've got Gibbs, Radcliffe Camera, Duke Humphreys, and the original university quad, Nicholas Hawksmoor's Clarendon building, and just next to it, Christopher Wren's Sheldonian. So nothing intimidating there. And you realise that Oxford, you look at the plan of the buildings around and all the colleges, there are all these quadrangles, and it just reminded me that Oxford is all about stuff that's hidden. It's about discovery. You get the odd look in, the odd glimpse. There's no big set pieces, really. And our project needed to be a bit like that. So the red square is the new Bodleian. And we visited a number of projects, and I show this one because we went around looking at various libraries, and this is a building that functions very badly as a library, actually. But it's one of those very, very few buildings in the world that I've been to where your spine tingles, and it's almost a spiritual experience. It's just breathtaking. The quality of light and the impact of this massive stack of books. It's sort of a temple to knowledge. So very inspiring, and I know inspired the British Library up by St Pancras too. So all we did really was take all the books out of the middle and create public open space inside it, a courtyard and exhibition space and so on. So purple is what we've kind of taken out, and then you see this courtyard inside, and there's a section here. So suddenly, from the university being very secretive about what's going on inside it, it's actually exposing its collections, opening itself to the public, and allowing people to understand what's going on. Quite a revolution, actually, for Oxford University. So here's just a couple of views. And externally, very little change, actually. Gilbert Scott, I'm sure you know, telephone boxes, power stations, that's Cambridge Library, that's a vent shaft in Liverpool, and the cathedral in Liverpool, he designed that aged 19. It was still being built when I was at university. That's not a comment on how old I am. It took 90 years to build, and it was just being completed in the late 70s. Actually, that's our building in the foreground, the Liverpool Convention Centre. So here it is as it was until quite recently, sometimes referred to as turning up to a dinner party in a tweed dinner suit, curiously, or more rudely as a municipal swimming pool. Because really it's a sort of keep-out kind of building. And this is south-facing on Broad Street, one of the prime streets in Oxford. So we've kind of got rid of this plinth and we're opening up this arcade. And that's really all the difference on the outside. It's got quite modest difference on the outside, huge amount of difference internally. The next thing I wanted to mention was sort of materials or materiality, if you like. They kind of mean the same thing to me, really. And a project in Wales done some time ago where we worked with slate, using 3 different slates on this National Waterfront Museum in Swansea. And the slate is, we're interested in the technology of how you can use these materials in an interesting way and an economic way. And what we've done is bond it effectively to precast concrete panels And then you can lift up great big pieces, and you brief the contractor to, you don't draw every piece, but you give them a set of rules and make them work to it. But it has a sort of, a warm quality to it, and a kind of grandeur, which I think we quite enjoy. To another stone facade, this is round the corner from the Bodleian in the Earth Sciences building. It's a new departmental building. So Earth Sciences geologists, basically. And one wall of this building, which is the wall as you enter the building, it's parallel to the entrance, is referred to as the narrative wall. And it's the idea of using striations and distortions that you get within rock. Speaks of what's going on inside this building. Again, stone fixed to precast concrete panels, and just using 3 different types of stone. But they're the same stones that are used on almost all the Oxford buildings at the moment. But it produces quite a sort of lively and interesting facade, which they love. I mean, the geologists just adore this building. To glass, still, we're great believers that buildings can continue to have very substantial areas of glazing. There are some architects who will tell you you've got to reduce it down to hardly anything for thermal reasons and for climate reasons. But I don't think it's right. If you engineer a building correctly, you specify your glass correctly, you can still have vast expanses of glass, which so affect the quality of the working environment for people. Deep planned offices and things, if you've only got tiny little windows, they become miserable places to work. And this is Guangzhou International Finance Centre. It's one of the tallest buildings in the world, at 435 metres. In front of this building you'll probably recognise, which is Zaha's Guangzhou Opera House. And another building you'll probably recognise in the middle there, I think, a concept by AA students at the time, the observation tower further down this main axis. So our building is mostly offices, but there's also a retail component to it, next to it, and apartments and so on. But the main building itself is offices, 70-odd floors of offices, and then the top 30-odd floors are a sort of 7-star hotel with an atrium going up the middle, which is, the atrium itself is taller than St. Paul's. So it's kind of mind-boggling space. And this is a view looking up the atrium from the 70th floor. And this sort of serration of the balconies was an idea that we wanted to mimic the diagrid form that we had on the outside of the building. And it seems to work quite well. The final fit-out, hotel fit-out, was done by hotel designers, but we got on pretty well, and they didn't. We didn't feel they corrupted our scheme. They really did kind of work with the architecture, and there are some amazing rooms in that building. Next, lightness and mass. We've always liked the idea that buildings and structures should have this quality of lightness, but I think so often the best way to show lightness is to contrast it with something that's more massive. The two kind of play off each other. But I have always been inspired by Naum Garbo's piece on the right, and you're just seeing it next to a bridge that we built up in Manchester to connect up with the BBC buildings in Salford. And I'm just showing you an unbuilt project. This is what's called the Old Pensions Building in Washington, D.C., which is the National Building Museum. An enormously scaled space. And if you look at the size of the people, I mean, it's just staggeringly big. Because it doesn't work very well as a museum, because if you're on one of the upper levels and you want to cross, you've got to walk for miles and miles to get to the other side. So they had this idea of, well, why don't we have a bridge that does something, that becomes an exhibit in itself. And we worked with Cecil Belmond on coming up with the idea of a tensegrity structure, a bridge that you could walk through. And the idea was that it would be made out of a series of glass tubes that were connected by cables. With tensegrity, no compression member directly touches another compression member. They're always separated by tension members. And you'd use stress gauges so that you could illuminate these tubes. As people walked across the bridge, you would be able to read what's happening load-wise, where all the loads are going. So here's the little modules that go together, and we developed this as this sort of idea that you could be light and massive at the same time. Because if you had a really light bridge that was sort of hardly there, then you'd lose it completely. It needed to have a presence, but it needed to be light, like a cloud is light. I think it was really, picked up on an earlier structure we'd done at the Science Museum in a Challenge of Materials Gallery, which is still there, and which itself was inspired by a sculpture by Ken Unsworth called Suspended Stone Circle 2, with just these 300 mil diameter stones suspended by a series of lines going back into the corner of the gallery. But lightness can also be, and this is really a point about contrast. I mean, obviously there's light itself, and colour. But the next building we did on the Jubilee line at Stratford was the station, which if any of you went to the Olympics, you would have probably gone through this station. And here this is about exploiting the kind of filigree of the structure against surface, where the surface is totally smooth. You're trying to eliminate everything that would otherwise be hanging down off that roof, so that you can just enjoy the light and the way that the colour changes, and to accentuate the lightness of the structure in front of it. And then I think a real recurring theme in our buildings is this sense of, well, the combination of movement and geometry. Movement, if you go back into Renaissance architecture, Borromini, I think, is a great example. This is his church, San Carlo alla Quattro Fontane in Rome. And then this Boccione sculpture, which has been on show actually at the Royal Academy with the bronze exhibition, where people are really trying to create this sense of arrested movement in their designs. And it's something that I enjoy and like to try and do in architecture, probably in not so sophisticated a way actually, because I really wonder how these guys designed the geometry of this church is just extraordinary. So this is a little bridge which you can see in London, in Floral Street, next to the Royal Opera House, connects up the Royal Ballet School. Just a 9-metre long bridge, which is all about, it's there for the ballet school, and it's there for the kids really, it's called the Bridge of Aspiration. They go over to the Opera House to use the facilities and meet the mature dancers, and it's a kind of little icon, if you like, in the street that says what they're about, while at the same time trying to talk about the movement of dance itself. And for us, one of the first projects that started as a sketch on the right, and then everything thereafter was done on computers, whether it's surveying, drawing, modelling, building. Here we are, this is the beam upside down that holds the bridge up. Every single aspect, even to the point where they had to model the lorry with the bridge on the back of it to see whether it would go under other bridges on the way to site. And they modelled the buildings on either side so they could lift it up on a crane and know that it could slot into place on a Sunday morning. Here's the, this is really kind of what it's all about. Really. To the other kind of literal movement, and of course the whole issue of, you can imagine the change. Turner's Rain, Steam and Speed painting, and then modern jet travel. But rain, steam and speed just signalled a sudden change in society where you could move, you could get out of your village, you could move around and go great distances and travel and so on, and was the beginning of what you might call sort of hypermobility, how we're all able to move, or lots of us are able to move all around the world. And technology, engineering structures, Crystal Palace, Galerie des Machines in Paris, things that we're very interested in, system buildings, but obviously it's the idea of creating interesting spaces, but we're terribly interested in how you do it, the mechanics of it, and ways of making it sort of rational and economic. And I think these were, Crystal Palace was, I think, the biggest building in the world built most quickly, just about ever. I mean, it's quite an extraordinary achievement. And some of our early structures, such as Stratford Market Depot, were very much in that sort of, that idea, influenced by Nervi, for instance. Then moving on to a project I just wanted to show you, because it's about a destination, which is really what the Singapore project is about. Of course, Gateshead Council had commissioned Gormley for this, which has been phenomenally successful. And we designed this Gateshead Millennium Bridge, which was built in its entirety pretty much, and then carried up the river by this extraordinarily large floating crane. And provides a spectacle, of course, of an opening bridge, and kind of is a 21st take on the harbour bridge behind, uses the same geometry and so on. But really the reason I wanted to show it to you, apart from that, the idea of a kind of refinement of design, and the big idea, if you like, that creates the destination, that people were going to this when there was nothing to see on the other side. They just kept going to it. But the refinement of sort of big things, big structures in quite big open spaces is a kind of step up from some of the earlier architecture we're doing, and how I was kind of brought up in the 70s in architecture, where you kind of tried to make everything as small and light as possible, that you start to learn to deal with quite big pieces of metal and make them elegant by sculpting them, which of course you can do because of computer technology. You can shape things and really study what they're like. So here's that quite big arch made to look ridiculously slender by just sculpting it so that the light is falling on it in a particular way, and then lighting and all the things that add kind of drama to it. So, cooled conservatories. Well, our story on cooled conservatories actually starts with the Alpine House at Kew Gardens, which was a delightful little project to do, but full of technical demands and architectural demands in a historic environment. Alpine plants, basically what they like is they need huge amounts of light, and they need to be kept dry, and it's really basically those two things. They need lots of fresh air as well. And the London climate is quite muggy, not dry. So straight away we're building a conservatory, which is the kind of opposite of the typical conservatory in this country, which is a nice place to visit on a cold day, and it's all lovely and warm, quite often very humid. So this is a conservatory that had to produce loads and loads of light and had to ventilate very, very well. This is Patrick Ballou's section from Atelier 10, who worked with us on the project, along with Dewhurst McFarlane. And you'll see at the bottom there's a labyrinth. And the idea is, actually it's very simple, that you bring air in through this labyrinth through nighttime cooling, and then you trickle it out through these little things here. They come out over the plants, which are down here. These bits here are open on either side, and it opens at the top, so that the height gives you the gradient to encourage the ventilation. So you're kind of separating out the heat gain, the warming from the heat gain, from the needs of the plants, all in a structure that is arranged to absolutely maximize the amount of light that gets in. So in a funny kind of way, it's not a particularly big building, you've got quite a big space for very small plants. So it became, the challenge in a sense became about, well, how can we get the glazing to admit the amount of light that's required? And it was huge amounts of light, over 90%. Even if you'd had a conventional mullion, you could not have got the amount of light transmission that was needed. So it became a kind of cable-supported glazing system. Worked out initially with Dewhurst McFarlane, and then an extraordinary Austrian, I think I got it right, Swiss company called Tuschnid. So you get this very high degree of transparency, also using low iron glass, but it occasionally needs shading if the sun's too bright. And the shading itself also helps with the ventilation. It separates out the airflows. So an incredible level of lightness, actually, by using a couple of arches to span over Now the plan form of the building, this is Patrick's brilliant idea of looking at the Barossa termite, and that they build their own termite mounds that have this very similar plan form to which, though very, very narrow north and south and broad east and west, and it's all about regulating the temperature within. The ants work to regulate the temperature to create the perfect conditions for reproduction within the termite mound, and it has its own ventilation system, and it's quite a staggering piece of design if you think of it like that. And that graph on the right, the blue is what the ants do by themselves, and the red shows how they can't keep the temperature. If you turned their ants' nest round the other way, how actually it would fail. So there's the GUI picture showing the ants. And they all work together to maintain those conditions. So ours have a very similar problem, basically. There's the labyrinth, and that's just powered by a couple of 100-watt fans to get the cool air out over the plants. And there it is under construction. So that project, the director of Kew at the time was called Peter Crane, or Sir Peter Crane as he is now. And he was on the committee for Gardens by the Bay project. And the Gardens by the Bay project is the bit that I've kind of highlighted here. Just to give you, for those of you who don't know Singapore, or have been to Singapore but don't necessarily recognise it in sort of from the air, this road here is the road in from Changi. So if you're coming in from the airport, you come over this bridge, and that's when you first see our building. All of this land is reclaimed land here, and the kind of historic downtown is here. I think the Fullerton Hotel is there. So this used to be the waterfront, but actually they've now built a barrage across here, and they're trying to turn this into a freshwater reservoir. So this was reclaimed in the 70s, and then not really built. Nothing kind of happened on it. So the strategy that the government has through national parks is to build this garden here and then develop the land around it, which effectively in the long run will pay for it, but also, of course, create the environment that they're looking for. So it was a competitive process. Several teams were asked to submit proposals for more than one site. There was one on the other side of the water too. Gustafson Porter, in fact, won that one, and I think are progressing it. And part of the brief was to have these two conservatories. And the team was Andrew Grant, from Grant Associates, Ateliers 1 and 10. So it's Patrick Ballou and Neil Thomas, who I'm sure some of you are familiar with, particularly with those two. So these are computer-rendered images, these are actually post-competition, but just to show you basically what I'm going to be talking about. These two conservatories, the one on the right is Cool Moist, since christened Flower Dome. The one on the left is the one on the right is Cool Dry. The one on the left is Cool Moist, christened Cloud Mountain. And obviously we always wanted it to have a significant presence at night. And then you'll also see in the background there these things which are Andrew Grant's great idea and made a reality by a combination of Neil Thomas and ourselves. And this is one of Andrew's earliest sketches of his idea for the garden, and it's basically, Singapore is famous for its orchids, epiphytes as they're called, which are plants that have hosts and they live on other plants. And the epiphytes have a particular pattern of growing where when they branch, there's only ever two coming off one. And he's kind of devised this whole layout based on a kind of path system that comes from that idea, with the conservatories at the kind of heart of it. And then fully evolved, that's the sort of the complete layout. And this end of the garden hasn't really been developed yet. You generally can enter it here, but you can also come along the waterfront, or if you're driving there, you can park here and walk along here. And the sort of basic principle in the garden, of the way it's organised, is that this is people and plants, and this is about plants themselves only. There's a kind of division between the two. And our first schemes were, we got very quickly to the geometry of these two conservatories, because we knew that we think about the obvious things. It's a hot and very humid climate, and we're going to cool these conservatories, so you want to minimise the surface area of the enclosures, because otherwise you're just creating a problem for yourselves. So we developed this kind of toroidal geometry with these fins that would hold up the glass that would sit between these. And then on the bottom right is Andrew's concept model for the presentation. But we had found, that we liked the idea, the client liked the idea, but we found fairly quickly as we had won, actually, a little bit later, that the amount of light that they needed to get into these buildings was a real technical problem, and that you just simply couldn't have big sort of plate structures that would obstruct the light. I show this because this is very much Andrew's concept, and I think to some extent has become the big icon of I don't really like the icon word, but I think it's suitable here. The super trees are the things that people really remember, and he was going to have dozens of them, but gradually they did get eaten away. I think there are about 16 of them now. But the basic idea of those was that it's like a pergola, and then you have the host for plants, which would, because of the climate, will happily grow on just about anything. Another view of that. And then we straight away, as we got our appointment, go into model making mode. We work in sketching, we're modelling, we're computer modelling, all at the same time. No one method tells you everything that you need to know. And developing the sort of ideas for these two conservatories. We knew that they needed to be separate. They're two completely separate climates, but we really didn't like the idea of having a single conservatory with some sort of partition down the middle, where one side is moist and the other side is dry. So there were hundreds of these models. They're usually quite simple, crude models that can be either kept in the office or taken on an airplane to Singapore. So that gives you a kind of overview of the whole complex. And in the distance you get the hint of why Singapore is what it is, why it's got all this money. It's trade, it's containerization, it's a major stopover point for shipping. And the underlying concept, we always felt that we knew we were doing these very big buildings, that there was a danger that they would be incredibly energy hungry. The two things that consume a lot of energy, cooling and dehumidification, both very, very energy hungry. But we soon realised and started to get our heads around it, and this really is Patrick Ballou's initiative, that we found that our client, National Parks, because everything grows so prolifically, and they're responsible for the parks, but also for all public planting, any tree anywhere in the public domain, they have to keep cutting stuff down, they have to keep trimming it, and they had huge amounts of biomass, waste biomass, which they were putting in landfill. And Patrick said, no, you've got to use this stuff. This is an energy source. It's a kind of free energy source, which is just being wasted. So the basic idea then of setting up a biomass plant as the energy, basically like a CHP for the energy source, and then coupling that with some clever ideas that Patrick had about using desiccant wheels to dehumidify. Desiccant is just the same as the stuff, when you buy a camera, there's a little powder in a sachet which keeps it nice and dry. It's just the same thing but on a bigger scale, where the incoming air has the moisture sucked out of it by the desiccant, and then you use waste heat to dry out that desiccant for the next cycle. So it's an extremely efficient way of dehumidifying the air. So I'll talk a little bit about the conservatories in each conservatory. So cool dry is the sort of pinky one, and cool moist is the greeny one. We kind of use that colour coding as we go through. But just to to link it to the intended climates for the displays, the plants that would be within them. As it happens, and I don't know how much of this was NParks' original intent, I don't think it was particularly, they're both endangered climates. The pinky climate is essentially Mediterranean kind of climate, so it obviously is the whole of the Mediterranean, but it also includes California, Chile, bits of South Africa, bits of South Australia. You soon realise when you look at this is where wine is made as well. So, and it just happens to be all the climates that produce wine. So we soon said to them that you had to have a wine bar in this building. And then the green is tropical montane. So it's basically it's very high up in the tropics. Cool climate, cool and extremely moist, but likewise endangered. And then the internal layouts of these were developed really, this is really Andrew Grant doing the internal layouts for the planting display, but working very closely with NParks, Dr. Tan from NParks, so that he gets the zones of various plants from various parts of the world and organise. And I won't go into which bits where particularly, but there are sort of, there are olive trees over here, there are sort of baobabs up here, and they're on different levels and so on. That's a kind of example of, 2,000-year-old olive tree. I mean, we did wonder, that one does read about people taking olive trees from Spain and bringing them back to other countries, but I can only say I think they were doing it with the best of intentions. It's not something I would encourage anyone to do just to have in their garden. But to give you an idea of the scale of these buildings, so here we're looking at a cool dry, 170 metres long and 87 metres front to back. So they're big single span spaces. I mean, one could have done something with columns, but it would certainly reduce the drama of the space, but also I think would compromise the flexibility of how it's used. So comparable actually to the Eden project. It's pretty much the same size actually as the Eden project, each of these. And tall enough at 35, 38 metres I think it is to grow sort of full size trees and plants and have things on different levels. Geometry, always been a kind of preoccupation of mine. I said at the beginning I can't calculate, but I still feel I have an ability to envision a geometry in my mind and sit next to somebody on a computer and manipulate it and get it to work in a way that I feel is rational. We tend not to work with kind of random forms. We have a preference for, I don't often think there's an underlying beauty in geometries that have a rationale or a regularity to them in some form, a reason why they are how they are. And this started out as spinning a parabolic form into a toroidal form, so you get that kind of disc-like form, and then leaning it over. The reason for leaning it over will become apparent, I think, in a minute. It ended up the geometry changed very slightly, but that was the basic concept, which gives you an efficient form with not too much surface area. So there you see it, and then you see it tipped on its side. Now the reason it's kind of vertical on the right-hand side there is because this is where the great view is out across the water. The waterfront is here. And this then becomes the area that you can control the shading from. And then the other building is, as I say, it's montane, so it's about these very kind of moist, verdant plant types. And that needed to be a taller building, and it was slightly more compact, so you can see from the dimensions there, it's a fair bit smaller, and quite a lot taller, 58 metres high. Now a single space, 58 metres high, of those dimensions, it's a huge space, and when you're in it, it's quite a, you really, if you get vertigo, there are places you shouldn't go in this building. And within it, we developed something which I'll show you a little bit more of later, the mountain in it, because different plants work better at different levels, but we also wanted to give that sense of, you know, the sheer height and variety of what it's like to be next to plants. So there's the basically the kind of geometry applied as a grid. You know, the origin of the toroid being somewhere way below ground, and how we made it work. Oh, I don't know what's happened there. Something very quirky has. I'll call that a PC to Mac problem, and hope it doesn't carry on. But it's just a drawing of what you've been looking at. So here you see basically the various components of the project. Cool dry with this vast expanse with these kind of often desert-like plants. Externally the gardens with the super trees and the two conservatories kind of popping up. Distinctive in an environment where there are lots of distinctive buildings. And then cool moist at the bottom with the kind of rather more extraordinary interior. In terms of the brief, this was the key thing that we had to have 45,000 lux hours. So we had to have more. That's what Eden was supposed to have. We had to have more than that in terms of the light transmission. And there's the data on relative humidity and temperature. So that's cool dry. And then cool moist, higher humidity, but similar amounts of light. That soon got us into thinking about the structure with Neil, getting rid of these fins, thinking about trusses, and then eventually moving to the idea of a very, very lightweight grid shell, which was then stabilized by a series of arches that sit above it. Now, one of the things that I was absolutely adamant about was that I didn't want people walking into this building and seeing structure. You know, that when you looked across the space, all you would see would be a load of trusses or beams, and you never see the sky. So I just felt very confident that if you had a light grid shell and had the structure on the outside, somehow the structure would disappear out of your sort of consciousness in a way. And it really does do that. Those are the various components then. And then we sort of sketched away and had lots of sessions with Neil and Patrick and so on about how to get the structure to work. I mean, we wanted it to have quite a sort of flattish back. And then the waterfront here, originally we had our structure bending in. Now Neil said you just cannot do that. So it got moved out onto the waterfront. And we always had to maintain a marathon route across the front of the building. So here you see some of the kind of, you know, we worked through lots of options, and I think some offices draw every option in micro detail till but we tend to discard the ones we think won't work quite quickly and focus on the ones that we think might work. So trusses and things that we felt, no, this just does not look right. Oops, sorry, it's jumped there. And that was kind of what was evolving, was the idea of the grid shell, and then Neil saying, well, actually, you're still going to have to brace it up all the way across here, because it's quite long and low. And then what started to emerge was the form that those arches would take. I think this is one of my sketches. Probably got some notes about some other potential job there on the right, which you should probably ignore. But that idea of, I just wanted to point this out, and the relationship between that form and the Gateshead Millennium Bridge, of how do you make quite a chunky arch look really skinny and elegant. And then the other key decision is the grid shell, and these are options really. Do we put an external grid shell with glass hanging off struts below it, with something else that might support a few cables or whatever? Do we kind of integrate the two? Or do we put a grid shell below the glass and then have to have some penetration through the glass? And then what eventually we did, and again I pushed very hard for this, was to have a kind of triangular profile that created the smallest possible shadow, but again looks as light as it can be on the underside. And here they are being made. Of course they're upside down there. Now for those of you that are interested in the minutiae of geometry and how you fit things together, this all became about when you've got a curved form and lots of straight elements joining, those hubs, no two are ever quite the same. You know, you have to have a bit of tolerance around here to accept these very slight misalignments in the way that things join up as a consequence of the geometry. And we made models with we have a big model shop in our office to aid the discussion, but also to aid the presentations to the client, and then developed a set of drawings for that. And this is working incredibly closely with Neil Thomas, because there are all sorts of issues to do with thermal expansion of steel and the way that the grid shell moves, and they have to take into account of. They're really very, very complex. But that, as it was erected, you can straight away, I think, you can see this point about the structure being on the outside, that you become aware of the sky, and that you really do get that sort of minimum sense of enclosure, if you like, because it's so light. Then it became a discussion about the glass, and what kind of glass, and how do we achieve the light transmission that we need. These two axes are quite important. Heat transmission. We obviously wanted to keep the heat transmission low. We don't want all the heat from the outside coming in, which we've then got to cool. And we want the light transmission high. And these are the various types of glass that you can get. Now, Alpine House was right up here. We wanted maximum light transmission. We didn't really care about heat transmission because we could just ventilate it out in open air. Didn't need any plant. But Gardens by the Bay needed to be way down here. We couldn't afford, we wanted to eliminate as much heat transmission as possible, but we didn't need quite as much light transmission as Alpine House. And then the benefits of shading. There were huge debates with the client about where the shading should be. They wanted the shading on the inside, but we were able to demonstrate that that's actually not very effective. These figures here, 374 watts per square metre. That's the amount of heat gain you're getting from the sun, but also the sky generally. As soon as you add partial shading on the outside, that starts to go down, and full shading, fully deployed shading, it goes way down. So that has an enormous impact on the amount of cooling plant that you have to have, and of course the sustainability credentials of the project. So if the shading had been on the inside, we wouldn't have been able to get down to those levels. So we then set ourselves a problem of how the hell do you do the shading on a building this shape. These dark grey areas are the bits that needed to be shaded, and this bit here facing the water is sufficiently concealed with the right orientation not to need to be shaded. The sun doesn't get onto it. And then we looked at all sorts of ideas about how to do it. There's one with kind of flaps coming up off the beams that could cut out sunlight. This is a little sort of deployable grid of misters, actually. Blinds that could come across, flaps that sit on the top there, and even the idea of misting, that you could, there's no shortage of water there, that you could apply a mist and that would cut out light transmission. And then even possibly internal fabric blinds too. I don't know where that is, somebody else might know where that is, but that's a project that was built that did have this sort of kind of mist thing. And all of those eventually were ruled out as not being viable. The craziest of the lot was to have a dirigible over the building that you could just move around to get to put in the way of the sun. And there was one where we knew we'd have to have double glazing, otherwise the whole thing would be running with water all the time. It's a bit like a bottle of beer you get out of the fridge, and immediately it's got water running down the outside. Of trying to introduce things into the cavities of glass, again ruled out as being not possible to maintain. Other kinds of blinds running up between, but these slots are tapered, which is quite tricky. So eventually we had the idea, well, what about the self-furling gear that you get on yachts, where they roll up their jibs? It's a very simple system. And we developed something that used that idea. I think this little sequence shows you, we're able to demonstrate to the client that you could do this to actually get pretty much 100% shading, and that actually you wouldn't have to do them all in unison. You could do areas depending on where the sun was, or do areas due to the sensitivity of what's below it. And this is what has happened. And we wanted to conceal where those blinds sat, and they ended up being in there. Actually, you can see them on that drawing there. So they're kind of concealed within the profile of the arches. So here they are when they're first starting to appear on the building. But actually, because they have a slight transparency, they do create a lovely effect on the light within the building, a kind of dappled light, which is a bit like standing under trees, where you get the shade from the leaves. So in computer world, here's one without and with. So in a way, there's our kind of systems, and they're all sort of designed and established how it's going to work. So it then becomes a case of kind of making it happen. The various bits of structure, the grids, the arches, and so on. Getting the glazing grid to work became something that took up a lot of time. We were conscious that if you developed a form where every single piece of glass was different, it was going to be hugely expensive. So we undertook a program of analysing the shape of every piece of glass to see what sort of repetition we could get. Just a reminder that the glass is sitting actually above the grid shell. These are Neil Thomas's sketches. And started to look at, with a kind of radial type structure, that you do get these bands of repetition. But for various reasons, that you do get tapers, but also you get a certain amount of taper. You get a tolerance within a square piece of glass that can fit into something that's not quite square. And these drawings were just to analyse the numbers of different pieces of glass, basically, to work on cool moist. And there, that just gives you the statistics. Cool dry was more difficult, because cool dry, the evolution of the geometry on cool dry, it started as the perfectly radial toroid and was then squashed, scaled in one axis, so that actually does create a distortion. And likewise, that needed to be analysed, and does have many more different pieces of glass. And all this is done really to demonstrate to the contractor what they need to do. There's also issues of slight deformation of glass planes. When you really study the geometry very, very closely, you find odd things going on with these structures. It's never quite as simple as you think it's going to be. And here they are arriving on site and being put up by a few more facts and figures about the size of the structure and so on. The glass bit, really, when you consider there's an awful lot of glass, surface area of 16,000 square metres on one building and 12,600 on the other, it was worth the time studying it and trying to get it right. The next thing was looking at rainwater shedding. In Singapore, they get vast amounts of rain in relatively short periods of time, and quite often on a kind of daily basis. And there's very strict rules about not having hidden gutters and so on in Singapore. You have to have the runoff, and they don't want things, snakes and things, lurking in the gutters, and mosquitoes and so on. So you have to get a kind of efficient runoff. And we had to study, for our own peace of mind as much as anything else, how rainwater would run off this building. So we did a kind of series of models. And this is the one that shows that the watershed, and then analysing the surface to work out where the paths are. What's the shortest way down for water to get to the bottom of the building from any one part, to see where the concentrations would go, of water would go. So that's what these diagrams are all about. And these are not done afterwards, these are done as part of the design. And then you get this kind of massive great gutter which you can see into and clean out all the way around the building. And I have seen it pouring with rain there. It's unbelievable how much rain there is. We had Arabs working as facade consultants advising on glazing systems, and we also had to look with them at devising specialist equipment just for putting in and taking out pieces of glass for construction, but also for maintenance, because eventually pieces of glass break. There will always be some that break. Studying all these aspects in details, where the penetrations through the glass go and how you lower them into place. So here you see these, an individual pane of glass, and it's kind of like, how do you get to it? Various sketches of that. And we came up ultimately with we had to add a kind of rail on the top of the beam, and you see that the kind of device has to run up on these beams. And there it is, you see it there. It has to be capable of its supports moving apart to follow the taper, and to be able to climb up the backs of the buildings, and to stay level, so that people can actually work on it. So it doesn't go up at a twist. It has to. It's quite a complex little thing, that, but had to be designed by the design team. So here we're looking at cool, dry again, and just a little bit about the kind of environmental strategies. This is where the plant room is, basically, the ventilation plant. And the basic idea is, you've got a very big volume, so you don't want to cool the entire volume. What you need to do is work out where the people are and the plants are. So all the cooling is done kind of locally at relatively low level. And you either, where there's an upper level, you don't have open balustrades, you have closed balustrades, so the cool air can be captured at that level. And then because of the stack effect, obviously you get an accumulation of hot air at the top, and you can let that go, you can let that out. And that keeps it kind of efficient. And CFD studies to prove to everyone, client and ourselves, that you can maintain the comfort level temperatures that are needed. So just another look at that diagram, which is about, just a reminder, the desiccant dehumidification, biomass as the energy source, linking the waste heat and moist air expelled through these super trees. So some of them are just for holding plants, but some of them are also part of the ventilation system. And the master plan, the environmental concept, which super trees are working with which bits of the building. There's also an energy centre for the CFD. That isn't that building. That's a little conservatory which they use to prepare plants to go into the building. And then I'll show you this graph because it's sort of part of our brief, what Denpark said, because to them this was new as well, the idea of cooling conservatory on such a big scale, and us saying we're really worried about the amount of energy, the CO2, carbon, credentials of this building. And they said, well, if you can have less energy usage than a typical office, well, he said, well, how do you compare a typical office with an enormous great conservatory? They just don't have anything in common. But anyway, what we actually managed to achieve through all these systems is that power generation on site using biomass, solar, and so on, you can see the various types up there, exceeded the consumption that we've got on site. So effectively, it's neutral. It's kind of carbon neutral, and net energy is zero. That just homes in on the same thing a little bit more. And we're using bits of various different things, a little bit of solar, thermal, a bit of PV power there, and the CHP, which is all biomass powered on the generation side. A couple of construction shots, and here's Patrick's plant room. Now we always like to rib the mechanical and electrical engineers on the vast amounts of space they take in our buildings, and I think you could have played five-a-side football in this particular plant room, but there ended up being a lot of kit inside it. And the point I was making really earlier about that, this is where the people and the plants are. So you deliver your cool air in these areas and not try to deliver it up there. So the vents, you're here, places like that. You've got ventilation there, and it just trickles out locally to get the comfort level. And I'm sure you've all heard of underfloor heating. This is underfloor cooling. So you're just pumping cool water through to keeping the slab cool. Is a very efficient way of doing it. So that gives you the kind of overview with the super trees and the conservatories with their various components. And just a few slides on the interiors, which I'd say we were in partial control of, not entirely in control. It's a combination of Andrew Grant, a bit of ourselves, and quite a lot of national parks and whatever they wanted to put in it. But we did start to introduce the kind of earthy colours to get a bit of warmth into it. And this is a very early drawing, but just in principle, so you kind of understand how it works. You come in about here at a lower level. This is a raised level, a kind of mezzanine within the space that is the sort of baobab grave, or bottle trees they are, which looks out over this space. This is true Mediterranean, olive trees, lavender, and so on. And this is the flower field, and they have changing displays in that field. They want colour, because they don't have an awful lot of colour in their own plants. And just a few images of it under construction. So these are areas that ventilate, that spill cool air out. The various bits of concrete structure within, all once the roof is on, so all that construction can happen while it's dry. That's the raised mezzanine. This becomes an area for dining. You can get, I think it's 500 diners in there, which is important from the economics of the whole thing. And during construction, plants are appearing from all around the world. Bottle trees and lines of things in small pots and so on that needed to be brought in before. There was nowhere else to put them but within the building. So there's not such a big difference between the kind of Andrew Grant's early vision of the planting and the reality. But it's a lovely place to wander around. I mean, particularly on a sunny day when you get the light coming through the grid shell, and there's kind of dappled light, and there's lots of places to explore, and you don't take it all in at once. You really do have to kind of wander around to get what's going on. And there's a view with the shades partially deployed. And then the space, what becomes the marathon route, I'm sorry, I've just pressed that button too soon. The marathon route in front of the building, where you get this sort of almost cathedral-like space of the arches coming up, and the views out over Marina Bay. Moving to the other building, the key to that was, obviously you've got to have the moisture, but we had this idea that we should build a kind of mountain in it, because it's a montane climate. I mean, it needed to give some perception of the height and the kind of variety that you get because of that. So we developed a structure on a series of levels which had internal exhibits, but also had routes out, and it has this big waterfall dropping from the top. They were very keen to have the biggest internal waterfall in the world, I think. Becomes an attractor. So there's an environmental diagram rather similar to the previous one. Really, just the points to note. I mean, again, delivering the cool air closest to where it's needed, expelling the hot air, making use of the stack effect and the differential in height. And then the form of the mountain itself evolved from something that occupied almost the entire footprint to something much more compact with a kind of ravine as well. So this is, in a sense, typical of the kind of environment that you would have in reality in the montane climate. And concept sort of development, the sketches of, well, how do we make this mountain? Do we make it a solid thing, or should we make it a kind of frame, a kind of slightly crazy frame? You've seen that, and you know those chairs that look a bit like that too, and models that we built to discuss with the client how you could have these kind of rings which would have plants growing within them and join them all up together. And the idea for the ravine right down here. And one's talking about a sort of 50-metre difference between those two levels. things that you see in nature that are kind of doing similar things, similar sorts of structures, kind of fungi. And that evolved into a structure where instead of being rings, there were a series of openings, and that whole concrete structure could then support the plants, become the host for the plants. A very early rendering of this waterfall and the moment of entry into the building, and then here under construction. And then from the inside looking out. So quite big scale spaces. And then what's applied to the concrete, all these systems, which is a combination of wires and irrigation, which you can then attach the planting to. And then we started to look at a series of walkways cantilevering out of the space so that you get a lift up to the top, and then you go on a journey down through and around the building, going out into the space periodically. These are just diagrams that show these kind of seemingly random ventures out into the tree canopy. Simple computer-based modelling to explore the geometry and form and so on. And then an image of one of those components of those bridges, which were kept as slender as possible, being lifted out into the space and assembled together. And then the first view of those cantilevered walkways, sometimes on cables, they're supported on cables from the grid shell, sometimes supported on struts coming out from the concrete. But that gives you the idea of the kind of height, the upper tree layer, that's kind of the highest bit that you want to see. And there are different things going on, different kinds of plants, different experiences at the various levels. Same CFD analysis. I'll press on a bit because I know I've been going on a bit. To get local cooling, to demonstrate that it works and that you're not losing too much of it. And then, pretty much in the final form of the mountain with all the plants on it and these various walkways that you can come out on. And when you're up there and you look down, I mean, it does seem like a long way down. But you also get views around Singapore too, of other buildings, particularly on a nice sunny day. Precedents in other places that people might visit. People like these scary walkways. They want to go. Some people won't go up them, but there's always people that see it as a bit of a dare and want to walk up spaces like that. And then at night, sometimes it's completely dry. Other times they turn on the misters, and they need the misters for the benefit of the plants, not just for show. But it's particularly spectacular at night. In the base of that mountain, as you go down through it, right at the bottom is a kind of theatre, and that's where they start to tell you the hard, tough news about what happens with temperature rising in the climate. What happens at 2 degrees, etc. You might get floods. How certain plant life ceases to appear. You even get the dead elephants here. As their environment becomes they can't survive in it. Floods. Well, I don't know if you have to wait till 5 degrees to get floods. We're getting the floods already. And starvation here. It's quite sobering actually when you see it. But it does end on a positive note that we could actually do something about it. As more areas become sort of sun-drenched, that you can develop systems for harvesting the energy and start to look at alternative energies than fossil fuels. So there's some positive things there too. So just to refresh again, this is Patrick's final diagram about the environmental systems. I won't go to any detail. It obviously evolved, to different kinds of, more familiar types of chillers and so on, steam turbines, biomass boilers, and so on. But the essence of the concept was still working, every bit as hard as we always intended. So just a few words about the super trees, which are very much Andrew Grant's concept, but Neil Thomas kind of worked out how to build them, and we did a lot of the detailing and actually took responsibility ourselves for one of them, the one that has a bar in it, as it happens, which is this one. You can go up this one and there's a bar Indochine at the top. It's a great place to go because you get fabulous views all around the garden, but they're also opening a roof terrace on the top. This is 50 metres across and 50 metres high. And a few sketches of, developing the ideas, well, how do you build this thing? How's it going to work? It's quite a sort of tricky structure to do. And this does demonstrate our working. We all sit together, we sketch out ideas, and then people go away and kind of work them up to see what works best. And in between some of those trees is this extraordinary walkway. This is Neil Thomas's design, and his, not ours. Again, not for the faint-hearted. I mean, you do feel very exposed. It is unbelievably light and just suspended from a series of cables that hang off the super trees. But it's quite a fun place to visit. And when you look up from below, I mean, I think there's some quite kind of spectacular. I love these kind of tree-like filigree structures and the transparency of the deck, the walking deck, contrasted with the plants and the palms and things below. They somehow are sympathetic with each other, the actual nature and then, in a sense, the false nature. And you get these odd patterns, just so you can see how they're made. There's a concrete core and a steel structure on the outside which then holds the plants. That's looking down the gap between the two. And then made here, you build the concrete column, slip-form concrete column, you attach the working bit, as it were, and you lift it up. So the whole tree is built on the ground and then hoisted up, and then the outsides get clad with the various other parts. The hub joining the two conservatories is another tricky area because the client wanted people to go to both conservatories or either conservatory, and you pay separately for them, and they're on slightly different levels. So there's an area where large numbers of people would queue. So we wanted to devise a canopy system. So we devised this sort of canopy system that goes back to Andrew's idea of the form of how orchids' stems grow. So here, section through the canopies, and then this is how Neil Thomas works. Annotating sketches, giving you sizes, and so on, and you then kind of work from that to refine and so on as you go. And there they are with kind of wooden slats on the underside and lit at night. And then we would have liked to have had more of this, but it got a bit cut down to cost, so we're having some coloured and patterned glass, which then throws interesting colour and shadows below. More of the same. So that's pretty much a roundup of what you're seeing. Now this is an interior of the Cool Dry, and it is used for events a lot, and it gets quite blingy at times. The Singaporeans, they do like they like bright colours and so on, and a lot of kind of razzmatazz and a lot of lighting. But the building takes it really well, actually. And cool, moist. This is the moment that you walk in, and it is really quite dramatic, this waterfall coming out in front of you. And at night, day and night. And you might just walk in when they've got the misters going and you kind of feel you're up in the clouds. Or you might be on a really sunny day and looking at the blue sky through this skinny grid shell. And I'm finishing really with just a few images of the project, so you're seeing the various components. And you do get these buildings in various views around Singapore. And there's a lot of very big buildings in Singapore, but you notice these because of their distinctive form and unusual purpose, actually. And of course the super trees stand out brilliantly. A view from across the water. This is pretty much what you would see if you were coming in from the airport. and looks particularly lovely with the reflections. And conditions are always changing. Or at night. There's a fantastic restaurant in there. This corner, Pollen, which has a restaurant here, have set up a restaurant in the building. And I can't mention the whole project without mentioning this building that's next to it, which is Moshe Safdie's Marina Bay Sands Hotel, which is has 3,000 rooms and is a pretty eccentric building but it has a casino next to it and very expensive shops and an enormous conference centre. And this is where the World Architecture Festival was back in November. We of course all went because our building's right next door, and were very, very pleased to win the grand award, the World Building of the Year. But I think a lot of people sort of love and hate this building, but actually, whatever one thinks of it, when you go up here, there's an amazing swimming pool, infinity pool, and that 60-metre cantilever is a bar. And it's one of the few places where you can go in Singapore where you can sit outside in the evenings and there's a breeze because you're so high up. It's actually a fabulous place to visit. And you look out over the city. And if you're going there, can I recommend that you ask for a room on this side of the building rather than the other side of the building? Here we are at the marathon route at night. Just a couple of other shots. And then, it's become this kind of focus. They have, people go there for their wedding photographs. The kids love it, they're all running around all the time. It's a party destination. And it's become a tourist destination as well. People go to Singapore. The average stay was 2.5 days, and they believe that this project will raise that to 3.5 days. Obviously, they're doing other things as well. They're not just coming to our building. But Singapore has quite a lot to offer. Food, restaurants, and bars are fabulous. There's not so many things to go and see, but it's a good place to be. And then promotions of, they use it to promote themselves. Not our first stamp, actually. We've been on other stamps, but it was nevertheless nice to get this. Good. So I will leave you with that. I hope that's given you a kind of understanding, at least, if not a very detailed one, of this very unusual project, which I think does show, even when one's presented with the, seemingly impossible tasks of providing a building that you think is going to consume huge amounts of energy and be the most unsustainable thing possible, that you can turn it round. And maybe it's a kind of new model in a way of looking at architecture. So thank you for listening.
Can we do a question or two?
Yes, of course. Yeah.
Thank you. Let me start with one, actually, Jim. I thank you so much for the presentation. Remarkable project, and the sort of scope and breadth of thinking. Truly amazing to achieve the ambitions of what you set for yourself. I'm wondering, in looking not just at this project, but things that have led up to it in your work, something that's very difficult to see from the images, but which I imagine being quite present in the unfolding of the projects, is a kind of command of how one assembles and erects to achieve this sort of a result. And I guess the question would be, how do you make that possible? I can imagine a first answer lying in the clearly collaborative group and the bringing in of not just the engineers but other forms of expertise. But I think it's the sequential delivery of what are in fact almost like total environments, which is a really interesting feature of them. And you almost, I would imagine at this stage, take it for granted. Nonetheless, it's a remarkable thing to see that somehow must be thought through to come to these sort of results. And I'm just wondering if you might say something about that.
Well, I think you touched on the collaborative point, that I think that we don't, as architects, we don't design things in isolation. It's not that we don't enjoy designing things in isolation. Of course we do. It's fun if you can be the master of everything and do it all yourself. But we have a genuine interest in what other disciplines are doing and how they work and what the days when, from our point of view, the days when we design something and hand it to an engineer and say, make it stand up, and then whatever they give you, that's gone for us. I mean, to us, it's all about, we want these sort of wonderful shapes and interesting forms, but we want every element to work hard. We want it to be there for a reason and to work hard to do a job, or maybe even do 3 jobs if possible. And that it does only come about, I think, from having that empathy with the issues that the other disciplines have to face, and being prepared to listen to them, so that actually we do sit together and design it together. And it isn't just, well, I want it that shape, and therefore it's going to be that shape.
At the other end of the extreme, I'm wondering if that also then, when there's an image you showed of the triangular sections in the shell, that it must also extend, of course, beyond the disciplines to the industries and
Yes.
the contractors and everyone else involved.
So there are conversations going on through the design with manufacturers, fabricators and so on. And sometimes we weren't allowed to do that on this project, but we were able to talk to British ones and just use our own experience of. But I mean, behind it all, I think there is, what I call, or what Le Corbusier called the spirit of the new. That's what's driving us forward all the time. We don't want to do what we did last time. We always want to find, and are always excited by new ways of doing things. It's easy to say it's backed up by experience, but of course it is backed up by experience. That you know what's possible, you know what's impossible, and you know what might just be possible.
Convince everyone involved.
And if you can, and then you've got to sell it. Yes, of course, you've got to sell it and convince people.
Can I open the mic
and
up?
have
Questions?
the answers.
Or a question, if I don't use the plural. Anyone? Now's your opportunity, without going all the way out to Singapore.
Deathly silence.
Can you elaborate on your sort of decision to go from a rectilinear glass layout to like a triangulated system, given the large spans?
Well, on the glass system, what was driving it initially was that you've got an economic size for the grid shell for the various elements that are in it to keep it quite small, and the best size for a piece of glass is about 6 square meters. So a piece that's say 2 meters by 3 meters is a pretty economic size in terms of the production, but also the use. So it's kind of comes from that starting point, and then trying to work back from that to see how to optimize it. Given that we have got, it's not triangulated; they're actually trapezoidal. They're all trapezoidal because they're tapering in. So it works from that premise, but obviously that itself, because the geometry of the grid shell is radial. It's coming out from these center points that are actually somewhere down below the ground. They're all converging, and we spent quite a lot of time looking at different versions of that, so that when they do converge and they get quite close, they're not so close that the piece of glass is sort of derisory. To get the taper right, so that the biggest pieces are a sensible size and the smallest pieces are a sensible size. I mean, it is a case of one thing leading to another. It is an iterative process to get that to work. It could have been a triangular grid, but triangular grids make all the junctions in the grid shell much more complicated, much more difficult to fabricate, even though you could probably make a grid shell that's more stable. Does that answer your question? Yeah.
If the design team as you described it at least, the kind of key part of the design team was very European. Let's say bringing European knowledge and experience to the site. How about on the production, fabrication, and everything else involved in the project? Just briefly to understand how that.
Yes, I mean it's a very good point, because it was we had counterparts in Singapore that were responsible for delivery of many parts of it, though we kept hold of the conservatory envelopes, the arches and the grid shots. We just didn't feel that we could let go of that nobody else would be able to mind it in the way that it needed to be minded. And in fact, there was a Chinese contractor that won the contract for the superstructure. And there was a moment where it became, I remember I had to go out to a meeting, and Neil Thomas came out as well, where it became clear that the Chinese contractor just simply could not analyse that structure to the point where you could be confident that they could build it, and they wanted to change the connections at the ends. And eventually Neil said to them and told the client, if you build it like this, it will fall down. You know, they couldn't do it. Basically, they were incapable of doing it. And I think that was basically just lack of familiarity with the depth of the analysis that Neil had done. So they changed steelwork contractor, which held things up for a little while. And then it was taken over by another one called Wohup, who was a Singaporean contractor. And that worked absolutely fine. The labour is all, as is common in Singapore, is imported. You know, that's what happens on building sites, big building sites in Singapore. And it's quite sobering actually when you see it. I mean, the labour for the Marina Bay Sands Hotel, they all lived in a compound of sort of porta cabins. You know, weren't really allowed out. It was quite staggering, actually, as an operation.
Another dimension of the project I was thinking about as you're presenting is the question of speed. You know, in addition to the expertise around logistics that almost makes it a part of the design work, in a way of integrating
Yes.
with the design thinking, the question of what sort of a challenge you faced in delivery. I mean, knowing something of the Asian versus European view on.
Yeah, no, there's a way of that they do get on with it. You know, on site they like to get on with it, and quite often you can be playing catch up, you know, and they're prepared to build things, and then if there is a real problem, they'll undo it and carry on. But whereas here, what's far more common is to try and resolve every last thing and then build. They don't work like that.
The overall time frame for this?
The overall time frame, I think, was about 5-6 years,
So
from start to
familiar
finish.
kind of.
Yeah, overall,
5-year, 6-year.
not that different, but the actual construction was pretty fast through. I think it was 3 years. 3 years actually on site. Yeah.
Jim, thanks so much for coming back.
Okay.
I really appreciate it. Thank you.
Thank you.
Thanks.
Thank you. It's a pleasure.